Okay, so yes, it's all visible. Yes, fine. So okay. Okay. Sorry. Technical. Okay, so last time I was in the middle of going through these different types of formal languages and the corresponding recognition by different kind of automata. So I'll try not to make this story too long, but let me continue with where I was. So I last time I covered the case of the final state automata and the fact that they recognize the languages, the regular languages, and type 3 regular languages. And then the next case is the context-free grammars that are recognizable by push-down stack automata. So I gave only kind of a graphical hand-waving description of what push-down stack automata are, like in the previous lecture, but let me just say a little more precisely. So the data are, part of the data are the same as the case of finite state automata. So you have a finite set of possible states of your automaton. Some of them are marked as being final states. And there is a finite alphabet, which you can think of as instructions that you read on the tape that tell you how you move around this graph. But now you also have another alphabet, gamma, which is the stack alphabet, which is what you can keep as a memory. So now it's no longer a memory-less process, but you can store something in memory. And then you have transitions, and transitions no longer go between one state and another state according to what instruction you read on your tape, so according to which letter of your alphabet you read on the tape. But you also read something, one letter that is at the top of the stack of the whatever. So the only thing you can read is the last thing that was put into the stack, and along with moving to a new state, you also deposit another string in the stack, of which the last thing will be the next thing visible that you can get out of the stack. And then again, there is an initial state that initializes the automaton where you are on the possible states, but you also initialize the stack. So that's the difference. And the transitions indeed are determined by what you read on the tape and what you read on the stack. So first symbol in the stack, and then a letter in your alphabet of the labels edges in the graph. And the transitions look something like this. So first of all, the configuration now of your automaton is the state in which you are, so an element in Q, and a certain string, which is what you have read on the tape, the instruction that you read on the tape up to that point, and what you have in the stack at that step in the calculation. So what you have on the tape, what you have on the stack, and where you are in the space of states. And given a transition, which is where you are, what you read on the tape, or just the top of the stack, where you move to, and what you deposit in the stack, you get a corresponding transition from a certain configuration of the automaton to a new configuration where you have moved, used one of the letters on the tape, you have moved to a new state, and you have deposited something new on the stack after using a letter at the top of the stack. And so a computation in your stack, push-down stack automata is a chain of transitions from one configuration to another configuration achieved by this sequence of transition of this kind. And again, this is the picture that I showed before, where now you have, again, a graph with vertices labeled by the states. of the automaton, but now the transitions are not, the edges are not just labeled by a letter in the alphabet, but also by what you read in the stack and what you deposit back into the stack. And so now there's two, but unlike the case of the final state automaton, now there are two different ways in which your computation can terminate. Either it terminates because you reach a final state in the space of possible states, but it can also terminate because you reach an empty stack. So you can say that your automaton accepts a certain string of instruction, a certain word in your alphabet by final state. If when you perform that sequence of moves in the automaton, you end up on a final state. And this is the same as what you have with the final state automata. But now you have also another way in which your computation can terminate. You can say that the string of instruction is accepted by empty stack. If at the end of that sequence of instruction, you have to stop because you have nothing to read in the stack. And so there are a priori two different ways in which your calculation can terminate. And there's one of the known results in the theory is that if you allow non-deterministic automata, so again, the difference between deterministic and non-deterministic is as for the final state automata. If you specify the state in which you are and the labels that you read, if it's deterministic, there's a unique state that you can reach that way. If it's non-deterministic, you have a choice of different states that you can reach with the same labels. And if you allow for the non-deterministic case, then recognition by final state and recognition by empty stack are equivalent. So you don't have to really distinguish between the two. They compute the same languages. But if you want to stick to the deterministic case, the recognition by empty stack has additional properties, and that I won't get into details of distinguishing. So now this part of the Chomsky hierarchy theorem is that the languages that are context-free are exactly the ones that are recognized by this push-down stack automata. So you want to say that, okay, if you start with a context-free grammar, then you can construct a push-down stack automata that will recognize that language. So you start with a given grammar with non-terminal, terminals, production rules, and the start point, about which you know that it's context-free. So the production rules apply anywhere where in the non-terminal that you are transforming occurs without a specified context. And you want to construct a push-down stack automata that will compute this language. So you can, the key here is that you use the terminals as one alphabet and the non-terminal as the other alphabets. And the transitions will follow as in the case of the final state automata, will follow the production rules of the grammar. But now that you typically have production rules that are take a non-terminal and give you something that contains some terminal and some non-terminal. And if you have something like this, for example, then you saying that this corresponds to an instruction where the terminal is what you read on is your tape instruction, and this whatever string of non-terminals remains is what you actually deposit in the stack at the end, and that allows you to actually keep in mind a certain part of the computation that you can fish out and use again, and that, for example, what helps with this type of recursion that are not where you need to keep some memory of a certain number of instructions. And so whenever you have a chain of a derivation in the context grammar, it translates in this way into a computation in the automaton that goes from a certain initial state of the automaton to a final state of the automaton. And so this is the basic idea of how the construction in this direction goes. And if on the other hand, let's just focus on the recognition by empty stack. if you have a language that's recognized by a push-down stack automaton by empty stack, then you want to construct a context-free grammar that will generate that language. So you have now what you have given is the the push-down stack automaton, and you want to construct the grammar. And so you want to say what the non-terminals are and what your alphabet of terminal, and what the production rules are. So you take as the non-terminal all these possible configurations of the automaton that have two states, and so when you specify just the two states and a letter in the stack, that's your non-terminals. And the start symbol that you add to that. So the start symbol is just allows you to initialize the automaton and the stack, and you can one production rule that you include is that all the states are accessible in this form, and these are going to be like intermediate steps of your calculation, and then. If you have a transition in the automaton that starts with a certain state and uses a letter in the alphabet and in the stack, and goes to a new state and deposits a certain word in the stack, you think of this word as giving you as the intermediate steps of your calculation in the grammar. And so in this way, you can construct the grammar, and all of these calculations are compatible with the property that you want from the grammar. So this is the basic idea. Now, I mean, I'm going to just discuss quickly the case of the remaining types. So I haven't actually very carefully defined what I mean by type 0, and I'm just going to do it now more precisely. And the context-sensitive one, I have sort of described what kind of production rules they have. But let me start with the larger class. So here we are, for these last two classes, we are dealing not with this much more restrictive type of automata like finite state and push down stack, but we're dealing with Turing machines. And you can find them again by having certain finite set of possible states, some of which are labeled as final, and a certain finite set, which is the alphabet of your tape, of which now you want to include a distinguished element, which is a blank symbol, and your input alphabet is the actual alphabet, does not include the blank symbol. And the transition now has the two states that you go from to, and a letter that you read and a letter that you write, and some movement that you can do on the tape. And then you sort of initialize to some initial state. So a transition is something that reads in this form, QA, Q prime, and then say L or R, let's say something like this. So what it means is that your Turing machine is in the state Q. It reads the letter A on the next square in the tape. This makes it change its state to a new state Q prime, and then it overrides the square with the new letter A prime, and then moves the tape one square either to the left or to the right, in this case to the left. So that's the basic functioning of
So where's the rule that says that Q will change to Q prime, which Q prime based on which A?
Yeah, right. So your transition is specifying this, right? So your transition is a subset here.
Oh.
So it tells you that your transition tells you if I'm at Q and I read A, then I go to Q prime, and then I override A with A prime, and I move my tape either to the left or to the right.
And it's a subset because you want to allow for multiple transitions?
Yeah, that's right. So you're gonna have like as you read through the tape, right? Each next thing you read is a new transition.
Okay, but I guess I should have asked her, is this still deterministic or you have multiple options because you want it to be indeterminate.
Yeah, that's right. So here you can also make the distinction of whether, if this subset is such that if I specify these two elements, then Q prime and A prime are uniquely determined or not. So you again have, the possibility of doing this, the completely deterministic or not. Okay. So in particular, when you want to describe what is a configuration of this kind of automata Turing machine, the configuration is given by the state where you are, the letter that is on the position in the tape that you are reading, and the configuration of the tape. Well, so you have two functions that tell you what is on to the right and what is to the left of the square where you are, and the configuration machine is all this data. And so in this case, the calculation is a sequence of configurations of the machine given by this form. And this sequence is achieved by a sequence of instructions of the type that I mentioned here. So of this kind of instructions of this type. Okay. So again, you can say that a word in your alphabet, which would be the actual terminals of your formal language, is accepted by this Turing machine if there is a computation in this sense in the Turing machine that it corresponds to this sequence of instructions on the tape. And so again, yeah, you have this. So now, what do I mean by a language being of type 0? So there are several characterizations in the literature that are shown to be equivalent. So I'm just gonna cut some and say that I characterize the type 0 languages as being recursively enumerable. So this means that you have a certain mapping of your set of words in the alphabet of the language to the natural numbers, a kind of Gödel numbering, so that the image of the subset of all the words in this alphabet that constitutes the language is a recursively enumerable set. So a recursively enumerable set is the range in the integer of some recursive function. So what it means, in other words, is that there is an algorithm that that exactly. So there's an algorithm that terminates exactly on the elements of that set. A stronger notion is actually being an enumerable set, which means that both the set and its complements are recursively enumerable. And in particular, the notion of numerable set and recursive numerable set are related to the notion of recursive functions. And these are a nice class from so this is just a basic theory of computation. So I'm just gonna flash through this quickly, but these are a nice class of functions which have very simple description in terms of simple generators and operations that you can make on them. So the primitive recursive function are generated by the successor function on the integers, and the constant functions and the projections, which allow you to extend to multiple copies of the integers. And you have some basic operations. You can compose functions, and you can do some kind of bracketing to form vectors of functions, and you have a recursion available. So any functions that's generated from this set of generators by repeatedly applying these operations is a recursive function, a total recursive function. And there's a further extension of this class, which is the ones that are called partial recursive functions. And these are, you also include an additional what's called a new operation, which is like a minimization function. And the difference between these and the total recursive functions is that these are defined on some domain. And so they are. This is part of church thesis that these partial recursive functions are those for which there is a program that terminates on the elements of the domain of this function, but of course it can run forever on outside of the domain. So they're just semi-computable in this sense. And so if you characterize the type 0 in terms of this recursive enumerability, then the recognition by Turing machine is basically built out of a few operations. There is this idea of assigning some kind of Gödel numbering that refers this to functions on the integers that are characterized by this recursive enumerability. And you can also translate things into sequences of zeros and ones, in the sense that you can assign to a tape description, the machine that given a tape description, else with a new tape description that is encoding this in terms of zeros and ones, and encodes the Gödel numbering, the corresponding Gödel numbering of a sequence in this way. And then, if you have a partial recursive function that has domain, the Gödel numbering of your language, the image, the integers under this Gödel numbering of your language, then you will have exactly that. The Turing machine would alt on the elements in the domain of this function, and it will alt with an output that encodes the value of the function. And so this gives you combine this thing that give you an explicit description of a Turing machine that recognizes this language. And so, of course, this it is just the relation between being recursively enumerable and being Turing, well, semi-computable in the sense that you can if the Turing machine stops, then the output is a word in your language. But of course, it could be that the Turing machine runs forever and will not stop necessarily. So, and the distinction between these very large class of the computable languages that are type 0 languages and the ones that are context sensitive is the fact that for those you restrict your Turing machine to have some bounded tape. So you have some symbols that mark the end of the tape on the left and the right, and so you don't allow transitions that cross this symbol, and that's okay. So I will not go into the detail of the proof for that one. I just wanted to give an idea of how this argument for the machine recognition of formal languages works. So as I said, I wanted to just to give some examples of getting a little bit more of the feeling of what these formal languages work, how these formal languages work. One can consider the examples that come from groups. And so you imagine that you just have a finally presented group. So you have a finite set of generators and you have a finite set of relations that determine the group. And so there is this famous word problem for the group, which is what are the set of words in a symmetric set of generators that would give you the trivial element in the group. And so in a sense, this is related to the question of when the words represent the same element in a given presentation of group. And also there is this general question, when is this word problem for group algorithmically solvable or not? And so the one observation is that this question is naturally formulated as a problem of formal languages in the sense that you can associate, when you consider, you can take the set of all the possible words that you can write in the generators of the group, and then in this symmetric set of generators in the group, that's your overall alphabet and all the words in the alphabet. And inside this, you can take as your language those words that are the identity in the group. So this is, so what kind of formal languages is it?
So can you go back?
Yeah.
What's the start?
What's the yeah, so these are just arbitrarily long words, finitely or finite length, but arbitrary length words in this symmetric set of generators. So for example, you can write a word that is x inverse, right? That, for example, would obviously be a word that is in this language, but So this is just any arbitrary word that you can write in the generators and their inverses. And now you just want to take those that are actually the identity in the group.
So any sequence that reduces to the identity.
That's right. Yeah.
But is there a reason that you are saying that the language is just the identity,
Well, I mean, the most general definition of a language in the sense of formal languages is, you have an alphabet and you take the set of all words of arbitrary length in that alphabet, and then a subset of that set is a language.
But why the subset?
Well, it's the words that are equal to one. That's a subset.
So I'm just trying to think intuitively, why is a language, a sequence of words that can, the relation between them is that they are reduced to some identity element.
Yeah, so I'm just defining a subset, right? I'm defining it by a relation.
Why? Why did you choose this definition?
Why do I choose this particular language associated to a group? Well, because this one is related to this word problem for groups, right? Which is an interesting mathematical problem on its own. So, but of course, yeah, you could say, I don't know, I take a subset of all the possible words, in the generator of the group, which has, I don't know, the generators that occur in a particular order. And I don't know. I mean, you could, yeah, those would be also formal languages, but I mean, this one happens to be related to a famous mathematical problem. So, yeah. Okay. So the question you can ask, of course, is once you define this as your language, what kind of formal language is it? And so there are two results that I'll list the references that are characterize the cases of the regular languages and the cases of the context-free languages. So one result is that this group language that we've defined this way that corresponds to the word problem for G is a regular language if and only if the group is finite. So that's a very restrictive class indeed. The finite state of the ones that can be computed by finite state automata can only be finite groups. Now the next step, in the hierarchy, what can be computed by push down stack automata is now a much more subtle class. These are characterized by being those groups that have a free subgroup of finite index. Like I made the example last time of SL to Z. That's a group that has this property. So moreover, right, whether the question of the solvability of the word problem is, you can thinking about what I just said of the recursive, enumerable recursive and case, this would be exactly the words that are recursive, right? So that the set and its complement are both partial, so they are total recursive.
In the second example, G can be not finite.
Yeah, that's right. The second would be, so of course the context free include the regular. So of course the finite groups are already included, but I mean, of course the characterization in terms of having a free subgroup of finite indexes for the infinite ones, for the ones that are not. So those that are context free but not regular are characterized like this. Okay. So, I mean, the recursive, right? I just said in words, meant that, this would be exactly the ones, the subsets of the set of all words in your alphabet, where the characteristic function that identifies the subset is an actual total recursive function rather than a partial recursive function. And so they are computable by a Turing machine that always halts and tells you whether it is in the language or not. Okay, so one thing that is interesting here is that you can actually this class of formal languages tells you that indeed this type 0 class does contain things that are not fully, there are these partial recursive functions, not just total recursive function. Because indeed, there are examples of groups where that have a recursively enumerable presentation, and there are recursively presented groups that have unsolvable word problem. And for example, you can construct an example like this where your relation depends on an integer that has to be in a set that is just recursively enumerable rather than enumerable. And so this looks like a kind of cooked up example, right? Because you sort of use the fact that your relations rely on a set of the integers that has an unsolvable membership problem. But the thing is that you can have situations where you have an actual nice finitely presented group that contains a subgroup that is of this kind, and then it automatically has unsolvable word problem. And that's the way that people constructed examples that look very innocent. Like, for example, you can have, this is like one of the first simplest example of a finitely presented group that has an unsolvable word problem. So you have an very explicit set of generators, very explicit set of relations. Yeah, the problem is exactly that it can contain a subgroup that has this unsolvable measure.
Out of curiosity, how would someone come up with such an example?
Yes, yeah, that's very interesting. So I don't want to get too much into the detail, but if you look at this paper, that's exactly how these kind of examples are being constructed. It's it looks like, okay, how do you ever come up with this kind of things? So by the way, all the slides are on. There's a web page for the class. That's linked on my web page. All the slides are available there. So. Anyway, so this is some of the references that discuss this relation between the word problem for groups and group presentations and formal languages and formulation of these problems in terms of formal languages. So let me say a little bit more, just to see how one does think with this kind of setting. So, well, the regular languages and finite groups is okay. If you have a finite group, then you can have a standard kind of presentation where you take a generator for each element of the group and you take the multiplication rule, right, for the relation. You can always do that for a finite group, and because that gives you a finite presentation. And so once you have it written like this, then the finite state automaton is obvious. It has a state for each element in the group, and it has an edge for each multiplication in the multiplication table. So the finite state automaton clearly recognizes a finite group, the word problem for a finite group. And the other thing is to show that if your group is actually infinite, then you cannot make the room for it for computing its word problem through a finite state automaton. And the point with that is that you can say, okay, if it's infinite, then there's going to be some words in your some element in the group that cannot be obtained from any word of length bounded by a fixed n. And so if you have a finite states automaton that has only your set of states, and there's no additional memory or anything that you can use, so what the only information that you can store is where you are in your set of states, then in a situation like this, it would mean that if you're trying to compute this element in the group, you would have to go, you would have to end up on the same state that you have already used for coding some other words before. So there's going to be two words that have two different prefixes that for which you end up using the same state to code them. And so this means that you're going to have at least an element that is not one, and that would be computed as if it were in the language. So your language doesn't correspond to the word problem for this group. Okay, so then what do you do for these cases? And well, so one thing that you can associate to a group is its Cayley graph. So you place a vertex for each element of the group, and you place an edge for each each relation that multiplies by one of the generators. It relates to element of the group by one of the generators. And so if you have any word that is the identity in the group is giving you a loop in the Cayley graph. Okay, so what you are trying to identify when you're trying to look at this language is all the loops in this, all the closed paths in this graph. And okay, the group acts on the graph, right? Just by moving around the points, and and there's a nice invariant metric that just counts how long is the path that connects to ends. So, what is the main idea for yes? Yeah.
If it was a free group, how would the graph look like? If the whole group was free,
Sorry.
if the whole group was a free group,
Yeah.
and you try.
Yeah, this would be yeah, that's right. So if it's a free group, right, you don't have any relations. So no, any word in your generators is not the identity. So and your Cayley graph is a tree, in fact, and you don't have any. So yeah, I mean, in a sense, this is saying something right about this context free. Because the free group is sort of trivial with respect to this. So free groups are kind of not seen with respect to this kind of property of looking for this language that corresponds to the word problem. So saying that the context-free languages are the ones for which the group contains a free group which is of finite index, it means that there's a big chunk of the group that is not seen by this language. And so what is left is sort of close enough to being something that would be computable by a finite state automaton.
So this is a problem with the finite state automaton, right?
That's right. So the thing is that the finite state automaton is not enough, right? Because you do have this infinite, you have words that you have to be able to keep track of words that are as long as to keep distinguishing words that are as long as they could be, which in a finite group. But the thing is that a lot of these words are actually not doing anything from the point of view of this language, because there's this very big free group contained that will never contribute something that's equal to the identity. And so in a sense, that's why you are in a class that's still close enough to the ones that's computable by the finite state automata. So that means in a sense, the step from finite state automata to push down stack automata is not that big a step in terms of machines. Going from there to a Turing machine is a much bigger step. And so the reason why this is not such a big step is because this big free subgroup is not really doing much. And so the way to think of this, that's why you do this thinking in terms of Cayley graphs, because in the case of the finite state automaton, you just build a graph, which is the group itself, right? And it has so here you cannot try to do the same. So you build a graph, which is the elements in the group and the generators that connect them, and now you try to see that that somehow here way to think of the context freeness of the language is that this graph is not finite anymore, but is sort of looking the same everywhere, which is exactly the fact that your production rule are context free. So you can kind of bound, uniformly bound locally this graph, and then it's sort of wherever you are, it doesn't matter in some sense. So one can think of it this way, right? So you're interested in these closed paths. So these closed paths give you some kind of polygons in this graph. So you start by kind of reducing these polygons to something as simple as possible. So you try to consider ways of triangulating all these polygons, so that you only have to worry about these triangles, and sort of the simplest kind of polygons. And then you also the thing is with this, whenever you have this kind of polygon and you decompose it into triangles where you don't add new vertices, you just take diagonals of your polygon to triangulate. And you have always some triangles that are kind of at the boundary, what part of the argument would be to kind of reduce by eliminating those that are at the boundary, and try to try to simplify this triangulation. And so the idea is this, that you try to reach a situation where you have a diagonal triangulation of all these polygons that give you the words that are the identity in the group, but that these triangulations can be done in a uniform way everywhere on the graph. So all the words that are labeling the edges of these triangulations have some uniformly bounded length. So you're kind of getting around the problem that the group is infinite and that you have to consider words that are of some infinite length by kind of going, cutting out all these triangulations where all of these only depend on words that are of some finite length. And so the way to do this is to say, okay, let's suppose that I start with a language that I know is context-free. So you want to show that indeed you can triangulate all of these all of these polygons in the Cayley graph with a certain bounded length. And you can think of having every production rule in your language sort of describing for you a way of subdividing a polygon, because you kind of subdivide a certain word into a number of chunks, which are the intermediate step of your derivations of the word in the language. And so this gives you, and the fact that it's context-free is exactly what tells you that it doesn't matter, these same productions apply everywhere. And so for that reason, you can have a uniform bound on how you do this, because it doesn't depend on where you are in the graph. And conversely, if you have this kind of uniform triangulation, then it means that your production rules can be made context-free, because you can apply the same ones with the same lengths everywhere. And okay, so now this is a characterization of the context-free class in terms of this property of the Cayley graph. And then the way that you get to actually rephrase this in terms of a finite index free subgroup is a bit of a algebraic trick, in the sense that, so what you try to do is to simplify the group. And you try to simplify it with a sequence of operations which preserve both the fact of being context-free and the possible existence of a free subgroup. And so if you reduce it by a chain of these operations until you get down to something that is a finite group. And so at that step, you already know that is in this class, because it's in a smaller class. And then at all the other steps, you will have a free subgroup of finite index, and the context freeness will be preserved. So these two properties will always be combined. So the way that one does, so you have to find some decomposition of groups. So there is a famous kind of decomposition of groups, which are called the HNN extensions, where you have two subgroups inside the bigger group, and an isomorphism between them that's not coming from the larger group. So essentially, it tells you that you can write, you can decompose, this. So you have a larger group that can be decomposed in this way, where you add the generator way, and that conjugates the other group. So you have. It means that you can use the generators of a certain subgroup A and an additional generator, and the relations are just the ones that are coming from these other subgroups. So it basically allows you to decompose the group into a part that uses generators and a part that you use as relations. Okay.
Sorry, is this the same as what you use in the von Kaplan theorem for like the amalgamation problem?
Yes, yeah, it's I think it's pretty much the same. I mean,
The notation is the same.
Yeah, I think it is pretty much the same. The way that you want to use it here is the fact of wanting to have a way of splitting your group into,
It's an intersection with matched.
yeah. That's it. So, and then, yeah, if you have in a accessibility series for a group is a chain of subgroups where each one of them is obtained in this way from the previous one by something which is a finite group extent. So at each step you're growing by a finite group. And okay, so here's the kind of relation that actually there is between these properties in the group. So you have a finitely generated group, is accessible if you have an upper bound on the length of any accessibility series. And now you assume that G is simultaneously context-free and accessible. So far, this accessibility property is just completely thrown in, pulled out of the hat and thrown into the picture. And eventually you want to show that it's actually automatically there. And so here it's just done so that you can do an inductive argument over smaller groups. Okay, so for now you assume that it's both context-free and accessible. And then you can do an inductive argument on this accessibility length that cuts down. And you can start with a finite group because at each time you're growing just by a finite group. And then the next step is going to be, so you show that at each step the context freeness is inherited and the existence of a free finite in the subgroup is inherited because you have a part that you use only as generators that is free and the other piece is finite. So it's going to give you a free subgroup which is a finite index. And then, okay, so these two properties now are combined and they all extend together for all this chain of subgroups. And now you just want to show that this accessibility condition was actually there to begin with, and it's not an additional assumption. And this is where you use, I'm not going to go through the detail of the argument, but this is where you use this characterization of the context freeness in terms of these polygons and uniform triangulations, to show that actually implies this accessibility part of the property. So this, yeah.
Can I ask?
Yeah.
From a linguistic standpoint, is there a clean way to think about what accessibility is telling you?
Yeah, no, of course, these are exactly a class of languages that is cooked up from a mathematical problem, but so they don't correspond to natural languages, but the reason, in a sense, it's more that these classes that's very explicit in terms of group theory, they give a better sense of what is the difference, what kind of step it is going from like the regular languages to the context-free, right? In terms of group, you can really think of it as being extending. So the regular languages are really like finite groups. And going from there to context-free is kind of like extending by free groups. So in a sense, I think it gives more of an intuition, right, of what this difference means in terms of more general kind of languages.
But you can't think about it like a clear example in natural languages where you might say this is that's play.
Yeah, no, I know there is. I don't think there's any like example of an actual model of a natural language in terms of formal languages that would be the word problem or subgroup. I mean,
It's really Dutch.
it's like, as I said, no, so far we haven't found anyone who speaks SL2C, but a native speaker of SL2C, but still it kind of gives a sense, right, of what type of structure it is to be context-free. Okay, so there's a lot of interesting connections between this formal language formulation of the word problem for groups and various kind of settings that are geometric. It's known that certain geometries have groups, associated groups that have a solvable word problem, algorithmically computable word problem, others that don't. And so there's a bunch of things that have been, done using this point of view of formal languages. For example, this class of automatic groups and so on. So this point of view is actually used in, for example, geometric group theory, like this, but as indeed is not a model of natural languages. Just that the theory of formal languages itself, it then takes on a life of its own, and it's just a mathematical tool that you can use, for example, in geometric group theory or in other settings like that. Okay, so one last thing that I want to say about formal languages before like moving, I'm sort of like trying to fast forward through 70 years of general linguistics. So I'm kind of, but so I want to mention another thing, which is again a kind of formal languages that have been used for quite a while to do computations in linguistics in this case, which are called tree adjoining grammars. And these are, again, formal languages, but in this case, they are built so that instead of maneuvering only strings as strings in a given alphabet as the language, you directly keep track of tree structures. And your production rules are acting on trees and changing the tree structure. And as a consequence, they're acting on strings. And in this case, you have a set of the way you build this formal language is that you have a set of basic trees, and these have some markings. And normally you have a marking in these tree adjoining grammars. You have markings both at the labels, both at the root of the trees and at the internal nodes and in the leaves, and you have, in particular, certain auxiliary trees that happen to have the same symbol labeling the root and one of the leaves. And so the idea of the kind of moves that you can make to generate structures with these building blocks is, so one of them is the typical operad composition, where you have a tree and you plug in the root of another tree to one of the leaves of your given tree, in this case with matching labels. But you also have another kind of operation in these tree adjoining grammars, which takes an internal vertex of the tree that has a certain label, and then uses one of these auxiliary trees that have the same label at the root at one of the leaves, and kind of expands that node to plug in an entire tree. So it kind of splits that node into two, and with the same label, and plugs in this other tree with the root and one of the labels labeled in the same way.
So how is it different from the first operation, the grafting operation?
So the one of them is, so the operand composition, you're plugging in the root of a tree to one of the leaves of another tree. So it's
One of the leaves.
that's right. So it's really like you think of say you think of the leaves as inputs and the root as an output, and so you can feed the output of one thing to one of the inputs of another thing. And so but then it's always root to leaf.
So it's a question of internal or.
That's right. Here you also are allowed some operations that search for an internal vertex of the tree and make, so basically you break off the tree at that internal vertex, and you plug in another tree. So it's again, like doing two of these operand composition, except that you do them in a strange order, right? Because you have already done one, you undo it, you plug in another one in the middle, and then you plug it back.
When you plug it back, if you remove it from the internal, you remove the whole tree from the internal node, and you put another one, what happens to the tree that was already there?
Yeah, no, it's like well, I don't know. I have like a branch node somewhere in between. Like I split
Oh, you split it,
you
so-
split that node, and then I plug in an entire tree, and then the upper part of this node goes to the root of this intermediate tree, and the lower part goes to the leaf that's marked in the same way. So it's really like you do two operand compositions, but you do them in the wrong order. You have already done one, you kind of undo it, and you plug something else in between, and then you close it up again. So it's okay, why do I want to do that? Why don't I just do the normal kind of opera that plugs in trees. And part of the idea is because you want to account for certain kinds of transformations in that on sentences and language that appear to do something like inserting at some internal vertex of a tree. And of course, this is like a proposal that got developed for a while. And for example, it was one of the ways in which so these as formal languages are in the context sensitive class. So for example, they can realize this kind of cross-serial dependencies that I mentioned that exist, for example, in Dutch and Swiss German. And part of this kind of strange substitution rule were supposed to account for things like that, where you have to sort of like twist the order of how things occur in the leaves, and you do that by this plugin in. And so this allows for having some of this context sensitivity without going to an enormously large class of constant context sensitive grammars, which would be too difficult to control.
So in the adjoining rule, the other way around, are you thinking of that as some kind of quotient? If you want to reduce this whole tree to being labeled by that same point.
Right. So I will actually come when I start talking about like this newer type of models where there you really think about extracting of trees and taking quotients rather than doing this insertion operation. But I'll come back. But anyway, so this was one of the methods that were used to actually have a class of context sensitive grammars that can be used to model some of these structures that languages exhibit that are not accounted for by the context free setting. And so that's it. So these are sure. So right, one of the examples is exactly that these allow you to produce some of these recursions that are not accounted for by the context-free cases, but are in the context sensitive, but they're not much bigger than the actual than the context-free. So they're not. They're these classes that are called mildly context sensitive. Okay, so this is pretty much all I want to say about formal languages. Now I just want to go a little bit more in detail to how the things developed after these models based on formal languages. I mentioned in my previous class very briefly these ideas of transformational grammars and minimalism. And I want to just say a little bit more about those now. So let me get to the next. All right, so as I said, this at this point we kind of things where by the say end of the 60s or something like this. So kind of moving forward. So let's see what the idea was to go from this picture with formal languages to the picture with transformational grammars. So let's take a step back just to the context-free class. So I've already, essentially used this in some of the examples that I showed of derivations in formal languages. You have a way of representing the production rules and the derivations in your formal language. Let's say in the context-free case. And you have a way of describing them in terms of a tree of derivations. So, of what one calls a parse tree for the context-free language. So, you have these are a planar tree. They're rooted. They are not binary trees. They have any arbitrary arity of the vertices. But the idea is that whenever you have, for example, a production rule that replaces a terminal with a certain string, then you think of having a piece of your tree which has this vertex that branches out to n vertices underneath, which are labeled by the corresponding elements of this word. And so the vertices are decorated either by non-terminals or terminals. The leaves in the end will be all terminals. It's just that you read off the leaves, the word that you're, so the T is planar, right? So there is an order in which you can read the leaves, and that gives you the string that is produced by this derivation. This is the same example that I showed before. And that's exactly what when you have a production like this, it means you have a vertex that has tree branching, and the leaves, the nodes underneath are labeled by what you have in the corresponding string, and so on. So
you can't change the order. Changing the order does not give you the same thing based on.
No, exactly. So these are ordered string, and so the planar embedding of the tree is important because you want to produce strings, not just sets of. So this will kind of change, in later on for reasons that I will describe. But at this step, one really thinks, as in this whole theory of formal languages, one thinks in terms of producing certain strings in ordered strings in the terminal alphabets. And so this, okay, for the fact that's difficult to see is that anytime you have a context-free grammar, then any derivation can always be represented as a parse tree in this way. And so, okay, if you have a parse tree, I mean, you can read off what the derivations are, but which vertices are below as the descendants from a given one, and you have at the end from the root to the leaves that gives you the entire string. So this is kind of a simple correspondence. So this representation in terms of trees, in particular, shows that there's very often an ambiguity in how you represent strings in terms of a particular context-free grammar, because you can have different parse trees for the same string. And of course, there are trivial examples, but for example, a somewhat less trivial example is if you take a language that consists of two kind of recursion, infinite recursions like this, there is a large set that belongs to both of these. And actually these two have sort of different parse trees. And so this set is going to always have like two different ways of parsing in this structure. So maybe I'll skip the details to actually prove that this is the case. But I mean, so you can have to separate your grammar for this particular example into two subgrammars that produce these two different recursions, and each of them produces an infinite number of these common sets of recursions, and all of them have ambiguous parse trees. So okay. So far, everything that I said about formal languages is formal in the sense that it applies regardless of whether these strings have anything to do with natural languages or not, including all these examples from groups and so on. So what about things that actually have something to do with actual languages? So, for example, okay, one thing, so here the idea is to think in terms of these parse trees. So for example, let's say we are generating an English sentence like this one, or the book is believed to have been written by the Aztecs. So you can think that you are generating separately two sentences. One is stating that the Aztecs have written the book, and one that we believe it. Right? And then these two get combined in some transformed way. So the first sentence has a noun phrase and it has a verb phrase, and these two are combined together. And the noun phrase has a determiner and a noun, and it has the verb phrase as an auxiliary, and it has the rest of the verb phrase. And the rest of the verb phrase is in turn a verb and a noun phrase, which is the direct object of this verb. Okay, so these are, and similarly, the second sentence itself has its own parse tree, and it has, a noun, a verb, and another noun, this combined in a noun phrase and a verb phrase.
So you're splitting
Hmm?
every sentence and every natural language is noun phrase or verb phrase or only English? This kind of.
Yeah, so here, of course, the kind of parse trees that you're constructing are language dependent, right? Because, they follow the way that your sentence is structured in a particular language. So, of course, if you, for example, because we are talking about ordered string, the word order follows here word order of English. If you would write a similar sentence in a language that has object first and rather than subject or verb object as say subject object verb, then it would be a different tree. So that's also part of the here, when one would, people were formulating things or using this kind of formalism, they were not trying to have like a language independent model that then is realized in one or another particular language, but each language would have, so it would all, they would, use a similar formalism, but the specific production rules would be specific to one language.
And is there a reason that people find it worthwhile to just focus on one language in this specific way and not study language independent trees?
No, I mean, in a sense, the thing is that the goal of this entire point of view of generative linguistics would be to try to understand how languages is generated in human brains, regardless of the specifics of one particular language. But of course, for quite some time, you try to model a specific aspects of the syntax of a specific language and try to abstract what would be common rules. So a lot of this formalism at this time was sort of focusing on or isolating specific aspects of the syntax of one particular language and try to see like what the formal properties behind that would be and compare these things. Like for example, these different recursion that occur differently in various languages. Would be like a way of trying to say in what ways this adapt to specific languages as part of trying to find what is a common framework, right? So here, like all of this, you can say, okay, now you have produced these two sentences, and now you start to make transformations on them. So for example, one of them gets turned into the passive form. Another one, you start to insert, one of them in place of an element in the other sentence. So you have this kind of insertion of a sentence inside another one. You have another transformation to a passive form. And then you have something that you can delete because it's already present in some other part of the language and it can be deleted somewhere else. Yes.
How many of the operations are commutative? So for instance, it seems like instead of like apply operation, but first you could say we believe the assets have written the book and then modify the second part.
That's right. So for example, you find again that there are situations where your chain of operations that lead to a certain outcome may not be unique. Although in this formulation, as I will say that what the kind of formalism in time, you do specify a certain order in which you apply transformations, but sometimes this is not a uniquely determined way. Just as in this context free setting, you had the possibility of having different parse trees or different production rules for the same thing.
But again, these operations seem so language specific that they just seem like if you try some other languages, just
no, exactly. So you can see that these are just wow. So this was actually one of the difficulties that we were very aware of at the time, like that you can cook up like I'll show some example. I mean, you can cook up like a very specific and long list of instructions on how you make certain moves and transformations that are very language specific. And then, you have to kind of justify this very large list of specific instructions that sometimes are common or not common between different languages and so on. So
But
indeed,
even the definition of the transformations, in some cases, I think in some languages, insertion might not make sense, and
that's
there's
right.
also standard
And,
version.
and you cannot, I mean, in some languages you would do, I don't know, the passivization in a different way, right, than you do it in English. So I mean, these rules end up being very, very language specific. And so in a sense, but anyway, the idea for this point of view is that you have two processes that are now kind of distinguished. One of them is the generative process of these three structures, and another one is the transformation that you can make on them. And and in general, you can assume, for example, that this was also a way of trying to get around this problem of identifying a class of formal languages that would be strictly larger than the context-free, but not too large, that would account for these different recursions. So instead of doing that, one could say, okay, the actual generation of the structure is done by some context-free grammar, which is manageable enough. And then on top of that, you actually have a bunch of transformational rules that will tell you what else. And so things like these cross-serial dependencies, for example, would then not be part of the structure building at the heart that's done by some context-free grammar, but it would come back. It will come later through one of these transformations that is then specific to those languages that have these cross-serial dependencies and not of other languages that don't have them. And so you basically have this base collection of trees, which are produced by your context-free grammars. And then you have additional data that give you certain markers that you can put on these trees to tell you like which parts are movable, which parts are not, and what type of moves you can make on the parts that are movable. So the transformation rules will take the form of some set of symbols, that tell you, when you look at the corresponding strings that are produced by certain parts of the tree, some of them would be blocks from moving, others would be movable, and would be some rule that tells you how to transform those. I'm not gonna, I'll just sort of quickly flash through some of these examples, just say what is the type of formalism that we're using, because anyway, this is not the way that that this kind of calculation are done anymore. But for example, when one talks about this passivization form, one kind of isolates certain part of the sentence that are moved, others that are inserted or replaced. And of course, this is very specific to how you turn a sentence into the passive form in English. If you write it for another language, I mean, the overall formalism might be similar, but the actual rules that you use would be different. And then, you have also to keep track of a specific order in which this transformation are made. They're not like arbitrarily interchangeable as order. Otherwise, you would get things that are not necessarily grammatical, not. And there is this fact that sometimes they're not unique, they're uniquely determined. And so but one of the ideas that was the part of this transformational grammar viewpoint was that there is like a deep structure, which is the underneath base trees, and then there's some kind of surface structure, which is whatever transformation you make on them. And in some sense that this deep structure should be closer to be something that could be formulated in a way that's language independent, while this surface structure is more capturing the language dependent part. But this is not entirely, it's never quite, entirely fitting, but at least it's where this idea of, this structure and surface structure was coming up.
This was Chomsky's.
Yeah, this was in the 1970s, been like a series of papers of Chomsky and other people that worked out a lot of examples of these transformations and tried to work out this idea of having separating out some kind of basic underneath context-free generation and transformational rules on top of them. So, for example, like coming back to our favorite language for counter examples. So if you wanna capture this Dutch cross serial dependencies, right? In English, you will have something like saw, here help, swim. But of course, in a language like Dutch, where you have this cross-serial dependency, you will have all the nouns coming up first and all the verbs coming up after in this crossed form. And so in terms of this type of idea of transformational grammar, you would first have the context-free grammar that generates something which is not the grammatical form in Dutch, but it would be actually more similar to combining the subject with its own verb. But then you would have some kind of transformational rule that would reorder things, and that would be language specific. Okay, so these are part of the literature on this point of view on transformational grammar. There's a collection of the papers from the 70s that have to do with this transformational theory that was re-edited recently, and there were people that actually tried to make more precise mathematical models of how these transformational grammars worked and so on.
So from this example already, you can see that there's reason the modern approaches might want to get rid of the planar embedding. Firstly, that's the most basic thing you should not impose.
Right, exactly. So the part of what one can already see in here, right, is that somehow the word order should really be part of this surface structure that depends on the specific language, but that underneath there should be something that in which the word order doesn't really matter. The structural relation in the tree are the important parts. So last thing I want to say before moving on to the last thing about this historical overview. I said a few things about the idea, how the idea of minimalism came in the beginning of the 90s. So in a sense, I was trying to simplify this idea of this transformational, these two operations of structured formation and transformations. I was trying to kind of simplify the overall picture of how these things would work. And one thing I want to mention is that before this minimalism was further developed in these last 10 years, there was a good amount of work that was done trying to make it the rules of minimalism computationally implementable. And so I'm going to just describe briefly how that was done, because at some point I'll come back to kind of comparing that to the more recent version. So again, one of the ideas was to try to capture some class that from the formal languages point of view would be more expressive than the context-free grammar, and would be able to capture some of the cross-serial dependencies that are known to occur in languages, and always also would have some kind of good computational processes. So for example, being parsable in polynomial time, and have this kind of semi-linearity property that I'm going to talk about in a moment. So what is semi-linearity? So a subset of copies of the non-negative integer is semi-linear if it is a finite union of linear spans. And the language is in a given alphabet is semi-linear. If you have if a language is in this formal language's sense of being a subset of the set of strings in a given alphabet is a monoid under concatenation. So you can look at monoid homomorphisms to the non-negative integers with the sum, or to copies of the non-negative integers with the sum. And so you can say that the language is semilinear if its image under any monoid homomorphism is semilinear in the sense that and so the context-free grammars have this property. So this is also kind of a nice computability, has nice computability effects, the fact of being semilinear. And the context-free grammars are known to be semilinear, and the three adjoining grammars that I mentioned are also known to be semilinear. So another class that has this property is called the multiple context-free grammars. These were originally designed as a way to capture more of these cross-serial dependencies than that are not context-free, they're context-sensitive, but basically is again an attempt to go just beyond the context-free without becoming too large. And so basically the idea is that you stack like a bunch of context-free grammars into a vector where all the production rule act on all of them simultaneously, and then you put them back in a way that you can create these cross-serial dependencies, but without having to enlarge too much the class. So it's like having a vector of context-free grammars at the same time, right? And so the production rules would be like for context-free grammars, but now you also have composition of functions on these vectors of context grammars that can combine some of them together, some of these together. Okay, so this class in itself was one of the things that people were looking at for generalizing the context-free class, but not generalizing it too much. It's kind of related to the three adjoining grammars. And okay, I'm going to stop here and I'll continue next time. The point is that these are actually equivalent in terms of generative, in terms of generative power, but not in terms of computational complexity. That there's a distinction there, but they are equivalent to a computational form of minimalism. So this was a way to try to show that this step from formal languages to minimalism captures. It's again a way to capture this going beyond the context-free case just enough to account for structures in language that are not expressible by the context-free case. The point is that it's more than that, and so it's a bit deceiving, this equivalence with multiple context-free grammars, because it's computationally much more efficient, the expression in terms of minimalism than its equivalent expression in multiple context-free grammar. So I'll finish this next time. So.